Welcome back, everyone. I hope that everyone saw some cool ads in between. We are going to be going back to our notes on investigating number sequences. Just before we went to an ad break, we defined common difference, and we spoke about a common difference being a number that is continuously added or subtracted between successive terms. We also mentioned that a common difference is the main property of a linear sequence. Now that we've spoken about linear sequences, I'm going to throw a bit of a spanner in the works. We're now going to look at unique sequences. So these are sequences that don't necessarily have a rule that can be applied continuously. These sequences have their own rule. The first one that we're going to look at was designed by a mathematician called Fibonacci. So let's have a look at his example. So Fibonacci came up with the pattern that goes 0, 1, 1, 2, 3, 5, 8, 13, 21, and 34. Now, at home, you might be saying, but you just asked me to look for a common difference. And if you're looking at the pattern that's behind me, there's definitely not a common difference. So, what was Fibonacci doing, and what is this pattern? We are now going to look at the board, and we are going to try and see if there's any sort of mathematical relationship that we can discover between these numbers. So, let us have a look. If I'm looking at the first few numbers, so I have 0, 1, 1, 2, and 3. If I was thinking about doing a common difference, there's a common difference of 1 between 0 and 1, a common difference of 0 between 1 and 1, a common difference of 1 between 1 and 2, and a common difference of 1 between 2 and 3. So we can see that there's no common difference between those numbers. So that means we're going to have to get a bit more creative. So I'm going to erase what I've done with common differences. And at home, I want you to think, are there any sorts of relationships between these numbers? Could I ask you to find the next few terms of this pattern? Okay, I'm going to ask you to look at it, and we're going to now see on the board how we can actually figure this out and what Fibonacci was thinking. So let's have another look at the board. If I look between the first three numbers, I'm going to ask us to look at this number specifically. So this is term 3. Remember, we earlier defined that terms are the numbers that make up a sequence. If I look at term 3, it has a value of 1. But if I look at the two terms that come before it, I can see that term 3 is equal to 0 plus 1. So 1 itself is equal to the sum of the two numbers that come before it. Let's see if that same rule applies to the next term. So I've got the number 2, and if I look at the two numbers that come before it, I have 1 plus 1, which is equal to 2. Let's look at the fifth term. So I have the number 3, and 3 is equal to 1 plus 2. Everyone, I'm hoping that you can kind of see the pattern over here. With Fibonacci's sequence, the term value is equal to the sum of the two values that came before that. So I'm going to say that again. Each term value is equal to the sum, so I mean adding the two values of the terms that come before it. So this rule is going to help me find the next two terms of the sequence. Let's write our next two terms down. I want to write down the next two terms of the sequence, And I know that each term is equal to summing the two that come before it. So the next term of this sequence will be equal to 21 plus 34. So we can see that the next term will have a value of 55. I am again going to find the next term, and I'm going to find that by adding 34 plus 55. And I'm hoping that everyone will agree with me that the next term value is 89. So that is the Fibonacci sequence. The next example that I'm going to show you is one using words. So the pattern that I've got behind me is just the word smile. So everyone give me a big smile at home because you're happy to be doing that. The word smile goes in a row. So it's smile, 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 going infinitely on. We've just got those 5 letters being repeated. Let's look at the question behind me and what this pattern is actually going to be asking me. So while we are all smiling, let's look at it. As I said, we've got smile, smile, smile going on and on and on. This pattern is asking me, what will the 222nd letter be? So you might be thinking, okay, well, how am I going to know that? If we look at the word smile, we can see that it is a 5-letter word. So this means I'm going to be using my multiples of 5 to help me find out what the 222nd letter would be. So if I look at the number 222, is 222 a multiple of 5? Not quite. But what is a multiple of 5 if I'm looking at a number that's close to 222? Yes, 220 is a multiple of 5. So 220 is a number that is a multiple of 5 that has occurred close to 222. And we can see that with 220 letters in this pattern, we would have had the word smile repeated 44 times. That means that the pattern will begin again with the 221st term and the 222nd term. This means that the 221st letter will be S, which means that the 222nd letter would have to be M. So, for that particular example, M is the 222nd letter in the pattern. Okay, so I hope that everyone's good with me so far. Take a sip of water. We're going to be looking at another example. This example is a hypothetical one. If you and some friends were going to sit down and have a study group. Okay, let's have a look at the next one. I hope you're all still with me. Wonderful. So this example is essentially saying that if you and a group of friends were to sit down at a table that seated 4 of you, there would be 4 of you sitting in the study group. Then if I were to add another table to the study group and add 2 more chairs, I would now have 6 people at my study group. Then what would happen if I added yet another table? If I were to add another table, I would then have 8 people sitting in my study group. So let's look at the next question. So I hope that everyone's happy. We initially had 4 people at one table, then 6 people at 2 tables, then 8 people at 3 tables. We're going to see if there's any type of pattern between the number of people with the number of tables. Let's have a look at the example. So this example is asking me, if I were to add another table, how many students would be able to sit down and study? So we've already discussed that at our first table we have 4 people. We have 6 people when we add another table. And then when I add a third table, we then have 8 people seated to study. This question is now asking me if I were to put 4 tables together. So let's draw our 4 tables. We would then have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 people seated. So I'm just going to draw a big 10 over here to illustrate that we would have 10 students seated for the study group. Wonderful, guys. So if our tables are going 4, 6, 8, 10, 4 students at 1 table, 6 students at 2 tables, 8 students at 3 tables, and 10 students at 4 tables. Is there a common difference over here? Remember that a common difference is a value that is continuously added or subtracted between terms. I'm going to use my common difference, and then we're going to discuss what the common difference is now, to help me with further calculations. So let's have another look at this example. We have discussed that I've got 4 people, then 6 people, then 8 people, then 10 people. If I'm looking for the common difference, we can see I've got a common difference of positive 2, a common difference of positive 2, and a common difference of positive 2. So I'm going to write up here, we have a common difference of positive 2. Now I'm going to erase this working just so I've got some space to show my working out for everyone. The question that has been asked of us is to determine how many students will be sitting at 10 tables. Now what we're going to do is try and find a mathematical rule to help me instead of me sitting and drawing 10 little squares, which would be a bit of a mission. So let's look at the mathematical rule that could help me determine how many students will be sitting at 10 tables. So at 1 table, I have 4 students. At 2 tables, I have 6. 3 tables we discussed we have 8. And 4 tables we discussed that we have 10. So I'm going to ask everyone to see if they can see a connection between the tables and the common difference. At 1 table, we can see that we just had 4 people. But for the second table, we actually added another 2 people. If I look at 3 tables, I'm sure that everyone will agree that we already had 6 people, and I added a further 2. So over here, if I'm trying to express my number of tables in terms of the number of students that will be seated, here I can see that I had 4 people. At 2 tables, I had 4 people plus my 1 common difference. And then we can see that for the next one, I've got 4 people plus 2 common differences. So if we look at the mathematical rule that can help us determine how many people will be seated at a certain number of tables, it's going to be 4 plus the number of tables minus 1 times 2. So for 10 people, we're going to have the number of people at 10 tables will be 4 plus the number of tables, which is 10, minus 1 times 2. So I'm going to have 4 plus 9 times 2, which is going to give me 22 people are seated at 10 tables. Thank you so much for joining us this far. We're going to cut to an ad break, but we'll be back with more examples soon. See you guys just now.